What if we started a clear interval for a root, but then while doing iterations, the function of c turns to be undefined? Check how to go about it here in Numerical Solutions to C problems. Before delving with an example, let's differentiate bisection from the previous method first. Say that we have a curve drawn on the Cartesian plane, where the root is as indicated. When we were working on incremental search method, we actually have to divide the interval into desired increments and compute in order to know which smaller interval to use in the next iteration. Although admittedly, this method is simple, it is time-consuming, so the bisection method shortens the procedure a little bit. In this approach, the concept is to cut the interval into half and totally disregard the irrelevant half. So we take x of 0.5 and then drop the first half as the root is found on the second half anyway. We are to look for the root of the function 3x cubed minus 4x less 5 all over 5x minus 2. That should be nearest the origin to the positive side of the number line. We are to stop when we reach 3 decimal zeros, and we are again to start with the whole numbers as initial values. Just like every method, start with the initial values, whereby we assume a value of 0, targeting the instruction that the root should be near the origin. By placing 0 as x, the function then becomes thrice of 0 cubed minus 4 times of 0 less 5 all upon the binomial of 5 times 0 minus 2, which results to positive 2.5. Next, we assume x as 1. The function then becomes 3 times of 1 cubed minus 4 of 1 minus 5 all over 5 times 1 less 2, which results to negative 2. Let's illustrate the interval in the number line. At x of 0, f of x is positive 2.5. At x of 1, f of x is negative 2. Assume a curve connecting these 2 points. Now let's start the bisection method. Mark the limits, where x of 1 is negative and x of 0 is positive, according to their y locations. Take the midpoint of the interval by computing the average. That is half of 0 plus 1, which is 0.5. Let's then identify where the point is at the midpoint. Plug 0.5 as x into the function, so we get 3 of 0.5 cubed minus 4 times of 0.5 less 5 all upon 5 of 0.5 minus 2. And this gives negative 13.25. This value shows that the assumed curve is far from the true curve. But just the same as we can still see a root within the first half of the interval. The negative sign of 13.25 means that the negative limit moves lower to 0.5, disregarding the upper half of the interval. Let's move on with the iteration using a table. Plug in the values we just solved earlier. A is 0 and B is 1. Their average is solved as 0.5, where the projected f of c is negative 13.25. This completes the first iteration. Continue to the next by checking the sign of f of c, which is negative. Thus, c replaces the right limit as it is the negative limit. This would show that a remains the same at 0, and their average is then half of 0 plus 0.5, which is then 0.25. Have this number substitute x in the function, coming up with rise of 0.25 cubed minus 4 of 0.25 minus 5, all over 5 times 0.25 minus 2, and this gives positive 7.9375. For the third iteration, we start by checking that the previous f of c is positive. So c replaces the left limit, and b would still be 0.5. Their average is then computed as 0.25 plus 0.5 all over 2, which gives 0.375. Have this average in the function, and have 3 of 0.375 cubed minus 4 of 0.375 minus 5, all upon 5 of 0.375 minus 2, which results to positive 50.7344. With positive 50 for the latest f of c, we replace a by 0.375, and b remains at 0.5. Their average is half of 0.375 plus 0.5, which gives 0.4375. And the new f of c then is 3 times of 0.4375 cubed minus 4 of 0.4375 less 5, all upon the binomial 5 of 0.4375 less 2. The result is negative 34.6602. For the next iteration, have a look at f of c, which says that c should replace b. A is still 0.375. Their average is then half of 0.375 plus 0.4375, which is 0.40625. Place this into the function to get rise of the cube of 0.40625 minus 4 of 0.40625 less 5, all upon 5 of 0.40625 minus 2. The result turns out as negative 205.563. The trend of f of c until this point isn't showing any closeness to the x-axis, but we try more attempts. With negative f of c, replace b with 0.40625, and a is still 0.375. Their average is then taken from half of 0.375 plus 0.40625, which is then 0.39063. The new f of c is then thrice of the cube of 0.39063 less 4 times of 0.39063 minus 5 divided by 5 of 0.39063 minus 2. This provides positive 136.185. The seventh iteration then starts with the replacement of a as f of c is positive. B remains as 0.40625. The midpoint lies on half of the limits 0.39063 and 0.40625, giving 0.39844. Have this plugged in the function to get positive 821.025. Persisting on the iteration, we use positive 821.025 as a signal that c should replace a, and b remains the same. The average of a and b is then computed as 0.40235, where the function becomes 3 times of 0.40235 cubed minus 4 times of 0.40235 minus 5. This is divided by 5 of 0.40235 minus 2, resulting to negative 547.035. F of c seems to get smaller this time. For the next iteration, C replaces B because f of C is negative. A still remains at 0.39844. Take the midpoint at half of 0.39844 plus 0.40235, which is 0.4004. The function then becomes 3 times of the cube of 0.4004 minus 4 of 0.4004 less 5 upon 5 of 0.4004 minus 2, giving negative 3,245.07. It seems like even with the ups and downs of the previous functions of C, the trend is actually going farther away from 0. For iteration 10, we replace B by 0.4004 and A remains at 0.39844. The midpoint is solved as 0.39942, and having this value plugged into the function, f of C becomes positive 2,209.14. The values of f of C now reach the thousands, so it seems like we cannot use f of C in telling when we achieve the root already. In this case, the other option is to have the convergence of A and B. This means that A and B should be the same value. All we can do is to keep on iterating until A is equal to B. So with positive f of C, we replace A by 0.3994 and B stays at 0.4004. Their average is 0.39991, giving f of C as positive 14,239.5. Now because of the positive sign of f of C, C replaces A, and B stays at 0.4004. Their average is then taken as 0.40016, and the new function of C is negative 8,268.9. You can see that A and B are getting closer to each other. For the next iteration, negative f of C makes B as 0.40016, and A still 0.39991. C is then computed as 0.40004, where its function becomes negative 36,617.7. The 14th iteration takes C for the new B as f of C is negative. A is still 0.39991. Their average is 0.39998, and the function of the average is positive 51,263.5. Since we are working on 5 decimal places, there are still a few more iterations to go until A and B completely converge. Iteration 15 then has C replace A because of f of C being positive. B remains the same. The average is then 0.40001, giving f of C as negative 128,161. Although f of C already grew exponentially, we focus on the convergence of A and B now. Next is taking 0.40001 as the new value for B, and A is still 0.39998. C is then computed as 0.4, where the f of C is 256,319. As they get closer, we can visualize the answer now. The next iteration takes 0.4 as the new A. Then B is 0.40001. Their average will come out as 0.4001 again, and f of C is negative 256,321. So the next iteration uses negative f of C to replace B with 0.4 0.40001, while A remains as 0.4. Their average is computed giving the same value of 0.40001 and the same f of c as negative 256,321. Having no change between the last two iterations means that we can stop and take the root of the function as 0.40001.